All right, guys, welcome to day 3 of our statistics notes, so Unit 14 for Algebra 2R. Today we're going to talk about sampling variability and simulations. We'll also construct a distribution of sample proportions as well as a distribution of sample means. So a lot of the data that I'm going to be using I had to generate myself because it's just me in the video, as where normally I would get a class set of data from each of you. But you'll see what that looks like in a minute, and hopefully that'll help you visualize what I would have done in class with the students that were there. So if I scroll back in my notes to what we did yesterday, we talked all about random sampling, and we had this whole table where I had 200 baseball players and their throwing distances listed. Now, yesterday we all came up with our own 10 throwers, found the corresponding distances from this table, and then we found a sample mean and a sample proportion. At the beginning of today's lesson, we're going to focus on that sample proportion. So like me, for instance, I know that in class with my students, I had a 0.6 as my sample proportion. So I'm just going to put a dot on the 0.6, and you can as well. Now, normally in class, what I go around and do is collect data from everybody, but obviously it's just me, myself, and I right now in my video. So if I pull up Excel, what you guys are looking at is a bunch of random generations that I actually just computed myself. So you'll see that each of these is a sample of 10 baseball players. It just says 1 through 10 because that's my 10 samples. And these are the corresponding distances of the throwers that I ended up getting. So I believe I have 24 data points in here, meaning 24 samples. I'm almost positive I have 24. I've also color-coded this Excel sheet so that anything that is 300 or higher is in red so that it stands out, because that's what's considered a good throw. So that's what that 0.6 was that I plotted, if you remember. That was my sample proportion of 0.6. That was my team that had 6 out of 10 good throwers on my baseball team. Okay, so I'm going to use this data to then take the sample proportions and plot them on that distribution. So like in class, if I went around, Joe could say he had 0.8. I just wrote 8 for right now for his proportion. Karanjak could say I had 0.7, and Ethan could say I have 0.5, and then Kaylee could say I have 0.4, and so on and so forth. And I would then be putting these proportions in my distribution. So again, these numbers that I'm calling out, this 8 is corresponding to 8 out of the total 10 that are good throws in that sample. 7 out of 10 were good throws. 5 out of 10 were good throws, and so on and so forth. Okay, so I just adjusted my screen, so hopefully I can do this so that you guys can see what I'm looking at for data and then plotting. And I'm just going to go through and plot each of these. So again, I know it says 8, but that's 8 out of 10, so that would be a 0.8. So I'm going to go ahead and plot that. Then a 0.7, then a 0.5, and then a 0.4. And again, this was mine from class. These 4 are what I generated representing what student data likely looked like. Okay, now going on to the next row, another 0.4, 0.7, 0.7, 0.5, 0.6, 0.3, 0.6, 0.5, 0.6, 0.3, 0.8, 0.6, 0.4, 0.7, 0.3, 0.4. This is a little tedious, but keep with me here. 0.6, 0.2, 0.5, 0.4. A lot of 0.4s. Got a 0.1 in there. 0.5. Okay, so I'm obviously going into the text, but it is what it is. This is my distribution. And okay, perfect. That's actually good timing because I was starting to run out of space there. Got a little dramatic at times. And there you have it. So those are my data points, and I believe there's 25, and we'll check that in a second. Because like I said, I included my one from class that I would have generated with my students, and then this should be 24 additional ones. All right, so before I start answering these questions and whatnot, let's summarize our data in this table where I have the sample proportion listed and then the frequency. So obviously I had 0 zeros, so I'm just not even going to list anything. I had 1.1, 1.2, 3.3s. Now I had a lot of 0.4s. 1, 2, 3, 4, 5, 6, 7, 8, 9 0.4s. 1, 2, 3, 4, 5, 6.5s. 1, 2, 3, 4, 5, 6. 0.6s. 1, 2, 3, 4, 5 0.7s. And then 2.8s, no 0.9s, and no 1.0s. Okay. Awesome. So I complete the table to the right based on my distribution. So again, each one of these points is representing a proportion of good throwers in one sample of 10. Now, using my calculator, I'm going to determine the mean and standard deviation of this distribution of sample proportions, which are p-hats. So every single one of these is representing a p-hat, and I will state my result on the distribution listed up above. And we're going to round to the nearest hundredth. Okay, so I'm going to grab my calculator. Okay, so this is where I hit Stat, Edit, and I'm going to clear out any old data. Okay, so left is L1, right is L2. So I got a 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and 0.8. Let me just double check that. 8, 7, 6, 5, 4, 3, 2, 1. Okay, great. So now, based on my data, my frequencies were 1, 1, 3, 9, 6, 6, 5, 2. Awesome. Now that I've done that, I'm going to do a little 1-var stat like what I would have done last unit. Perfect. I already have a frequency list in there for L2. If you don't, you would throw that in there, calculate, and there you have it. So it looks like our mean is 0.5, so I don't have to round that. Oops, I don't need to write in the highlighter. My mean just happened to work out to be 0.5. And my standard deviation is 0.17. So your upside down baseball cap, 0.17 to the nearest hundredth. And there you have it. So what I did was I found the average of all of those sample proportions, which looks like that would be like the middle of our distribution. If I had to describe the shape of this, it looks like it's approximately normal. Okay, I'm just going to erase that. You don't have to draw that, but it's nice to use to describe this. Actually, that wasn't bad. Yeah, it looks approximately normal. Okay, and our standard deviation, which is the distance from the center, the average distance from the center, is 0.17. So I said this earlier in the video. What does each dot represent? That is the p-hat. That's the proportion of good throwers in a sample of 10. So what I'm noticing is obviously the most often happened was the 0.4, but I got a variety of different answers too because everybody got different samples. So based on the classroom data, what would be the best estimate of the true proportion of good throws? So what I mean by that is this is obviously a collection of a bunch of samples from our class. This gives me an idea to make an inference about what the true proportion is of all 200 baseball players if I were to look at that. So if I had to do a best guess, I would use my mean of my sample distribution, so that would be 0.5. So I guess about half of the baseball players are good throwers. Is the above data categorical or quantitative? Because this is success versus fail, you're either a good thrower or you're not, and we're talking about proportions, this is categorical data. So the reason why each of these, or each of you, I should say, had different sample proportions, which we generated yesterday, was due to something called sampling variability. And the entire dot plot that we just constructed is called a sampling distribution because it shows the distribution of the samples you took. So it's a kind of tedious process. Oh yeah, I meant to check here. How many total dots did I end up having? I think it's 25. I should have said in my calculator. Oh, I had 33. Well, apparently I did way more data than I thought I did. So I actually had 33 total dots. That's pretty good. So 33 total p-hats in my distribution based on my work here. Okay, now imagine if you wanted to get 100 of those. Super tedious, take a long time. What if you wanted 1,000 of those? Okay, that's where something called simulation can be really helpful for us, which we'll discover on the next page. So, how do we use our data to best estimate the true population proportion of good throws? We can simulate this process using technology. So we will use a tool called simulation to estimate the true population proportion. So that's the true proportion of good throwers out of that original 200. The word simulation means to imitate a process. All right, so I'm going to go to a website now. Okay, so I split my screen here. On the left, I have a website called Rossman Chance, which is a simulator. So again, this is technology that imitates a process. The right-hand side is our notes. So I'm going to be jumping back and forth between the website and our notes, so hopefully I don't mess this up. Now, just to give you an idea of what a simulator is, this guy can simulate, let's say, tossing a coin. We know the theoretical probability of getting heads when tossing a coin is 0.5, which is why they have that listed here. So that's basically representing the population proportion. Let's say you want to simulate tossing a coin 50 times. Now that's dramatic. Let's do like 20 times. And I want to find out the proportion of heads that I would have in those 20 tosses. So rather than sitting there and literally flipping a coin 20 times and recording your answer, the simulator will do it. So you'll see in the animation, it's flipping and then it's sorting. Now the animation's a little bit slower than the actual results, but you'll notice that I ended up with 10 heads and 10 tails, which means that the proportion of heads was 0.5, which is why you're seeing a dot right there at about where 0.5 is. And then I could draw samples again. That would give me another dot. Looks like another 0.5. It's kind of freaky. I'm going to turn off this animation. Give it a chance to catch up. It's a little bit laggy with the animation turned on. But you'll see that I start to get some variability there. Because as you know, when you flip a coin, you won't necessarily always get 0.5 every time. You'll get, you know, some variability. So each of these dots is representing a sample of 20 flips and then recording the proportion of heads. And obviously the more samples I do, the more filled in it gets, which is what you guys were witnessing when we were doing it by hand with the baseball players. Okay, so let me reset this. So here's how I use it to help me estimate the true proportion of good throwers in our baseball data. Remember on the previous page of our notes where we actually coincidentally ended up discovering that the mean of our sample proportions was 0.5. Now, I'm going to say this right now, in different classes we may have gotten like a 0.46 or a 0.48 or a 0.52. Like, whatever our data is, it could vary from class to class because, again, there's sampling variability. But if I'm being true to what we just did in the notes, we found that the true population proportion, or excuse me, we found the mean of all those little samples that we got was to be 0.5. So that means I'm actually going to just leave 0.5 there, because that's going to be what I use to be like, okay, so let's assume that 0.5 actually is the true proportion of the population. I'm going to now generate 10 tosses, or 10 baseball players really is what that is. And then I'm going to repeat that 33 times. So let me repeat that, okay? So assuming that the theoretical probability of getting a good thrower is 0.5, this is going to simulate me getting 10 baseball players, just like what you guys did, figuring out the proportion of good throwers, finding that proportion and plotting a point, and it's going to quickly do it for me 33 times. And we'll see how my data here compares to the data that we did together. So I'm going to hit draw samples, boom, and then I'm going to turn on my summary statistics, and there you go. So you'll notice that this doesn't perfectly match, and it's not intended to, because again, this gives you the assumption that, you know, the true population that you're pulling from everybody is 0.5, but in practice, it might not be exactly 0.5, it could be a little bit off, which is what you're seeing. And then the standard deviation was 0.141. So this distribution doesn't look too terribly far off from what I did in class with you guys. This is obviously a little bit shorter, and then this one's taller. Like, I think these were flipped, but generally the same idea. So I'm going to take this data and copy it over here. Now, for mean of all p-hats, from this I want you to write 0.521, and the standard deviation was 0.141. The number of samples, so that's how many dots that I put here, was 33, so that I could compare it to what we did in class or in this video. And the sample size was 10, because each dot is representing 10 baseball players and then the proportion of those that are good throwers. What if I change the number of samples? So let's say instead of 33, what if I want like 300 total samples? Okay, so let me reset this. Okay, I'm going to keep this at 0.5 because that's based on my data from the previous page. I'm going to keep it at 10 because, again, I'm picking 10 baseball players, but instead of 33, let's do something like 300. Okay, obviously these dots, there's so many of them that they almost look like straight lines, but there's your distribution, there's your normal curve there. So the mean of all the p-hats is about the same. It's about 0.504. It's about the same. I mean, it's obviously like there's a little bit of variability there, but it's about the same. And the standard deviation is 0.164. So again, not too terribly different from what I had before, and this was still with the sample size of 10. So again, what I'm doing is I just increase the number of samples. Now, if I want to go crazy with this, guys, I could just keep hitting, where's that button? Draw samples. Draw samples. And you'll see right here, it's keeping track of how many total dots I have in the distribution. So I'm getting kind of ridiculous here. All right, I got up to 10,500 samples. You'll notice, oh my God, look at that. It hits right at 0.5, and then the standard deviation is 0.157. So you'll notice that, yeah, like maybe it gets closer to 0.5 as time goes on, but still relatively the same, and the standard deviation at a certain point starts to be relatively consistent as well. There's probably some variability, but it's almost negligible at this point. So in comparison to what we did in the notes, so think about this again with the 33 and that mean and standard deviation. If I go back up here, okay, my standard deviation was 0.141. This one's 0.17. Okay, with this one it was 0.157. Over here it's 0.164. So again, it's like about in that same range, off by maybe a hundredth or two, but relatively the same. So let's actually continue filling this out. So our generalization here is that as the number of samples increases, the mean remains about the same. So that squiggle means about or approximately the same. And the standard deviation remains about the same. Sorry, my handwriting is awful right now because I'm writing on my laptop while it's like vertical. So I'm like writing perpendicular to the screen right now. By increasing the number of samples, the sampling distribution takes on the appearance of a normal curve, as I just explained, centered around the mean, right in the middle over here on the left. Okay, so back to the drawing board. I'm going to scroll back up. And I'm going to reset this again. Okay, so let's go back to doing those 33 again, just to show you some comparisons again to our classroom data. So I'm keeping this at 0.5, this at 10, and then this at 33, and then I'm drawing samples. Again, just to compare to the 33 dots we did in class. See, I got something a little bit different, but still about 0.5. My mean of sample proportions is 0.497, which, by the way, these should be little p-hats there. That was a mistake. Okay, 0.497. My standard deviation is 0.140. So again, if you compare it to what I did on the left or even on the previous page when we did it together, okay, about the same. Our number of samples was 33. Sample size was 10. Now let's change it where now I'm going to keep the number of samples at 33, but let's increase the sample size to 100. Okay, so I'm increasing the number of baseball players per sample, which I realize out of 200 baseball players, that's like half your data, but still, let's just say, okay, I increase the sample size to like 100, okay? Let's see what happens. So again, I'm going to reset this. So start over. I'm going to keep this at 0.5 because I'm assuming that's the true population proportion. I'm going to change this to 100, but I'm still going to generate 33 dots. So number of repetitions is correlating to my number of samples. Okay, so my mean is still about 0.5. But my standard deviation changed to 0.042. So again, as my sample size increased, oops, sorry, I'm highlighting the wrong thing. As my sample size increased, look what happened to your standard deviation. It went from here to here. So did it increase or it decreased? You should be thinking it decreased. So as our sample size increased, our standard deviation decreased. And that's what's great about increasing your sample size. If you honestly want to get better data, you want to go out and get data that's going to be more consistent or more tightly around what the true center is, the only way to do that is to start over and increase your sample size. So in general, we will say as sample size increases, the mean still remains about the same. But the standard deviation decreased. So that gives me less variability in the samples because all my data points are now more tightly around that center. And that's where I have this little visual here where it says higher sample makes it tighter together. So this would be representing my data with the sample size of 100, as where this was more with my sample size of 10, where there's a lot more variability going around. So a lot more wiggle room, if you will. So this is just a little snip of an example that I would have done in a previous year with some data, or even just a previous simulation that I snipped. As the shape of a normal distribution appears approximately normal, no matter what, our mean then is going to end up being our best center. All right, so big takeaway here. If you want to keep adding samples, like even if I did this over here, just keep adding samples, you'll notice the mean and standard deviation still remains about the same. The only way to get this much lower is if I restart let's say I make this like 200, you'll notice it got even smaller. Okay, reset. 500. Even smaller. So increased sample size decreases standard deviation. So it just makes it go more tightly around the center. All right. So the last little bit here is now to take a look at what a distribution of sample means would look like. So what we did up here was a sample distribution of sample proportions. So each of these are representing p-hats. So what would a distribution of x-bars or sample means look like? So let me pull up something else I want to look at. So let's do this. All right, so what you guys are looking at is a sheet of piles of M&Ms. So in class, every one of us would have received this same sheet. There are 100 total piles in here, and they're actually all labeled 1 through 100. And you'll see there's varying amounts of M&Ms per pile. I want to figure out what the average number of M&Ms is per pile. But I don't want to add up the totals of all 100 because that's just going to be tedious. So that's where we're all going to come up with samples to help us best estimate the true mean of the M&Ms per pile on this page. So if I go back to my notes here, that's what this is all explaining. Okay, so let's create a sample distribution of sample means from the entire class using our random number generator from our calculators. So ultimately, you will determine if you visually acquired the sample mean is truly representative of the mean of the population of the 100 piles. Okay, so we did this in class with the baseball players, so same idea. Okay, I'm going to do, and at this point you guys are all seated differently, so you guys would have all gotten different data anyway. If I go to math, probability, rand int. Okay, now mine isn't prompting me, but some of you guys will have a prompt. My low number for M&Ms I would pick is 1. The high number is 100. And then per one of these samples, I'm going to generate 1, 2, 3, 4, 5 data points. Okay, now I don't want to repeat, so I'm actually going to do like 7 in case I need to throw something out. And there you go. So I'm getting 95, 91, 15, 52, 41. And I don't think I had any repeats in that. So those are just my data points that I would hit. So this 95 that came up is representing pile number 95, which is down here. And there are 6 M&Ms. So if I go to my notes, okay, this was 95. And this was 6 M&Ms. My next number was 91. Here, I'll just list this out. 91, 15, 52, and 41. Okay, and then I go to my sheet and I'd find the number of M&Ms per pile. So go to my sheet. Okay, 91. Looks like he has 3. 15, he's up here, 3 by 3 is a 9. 52, it's like a little Where's Waldo here. Okay, 3 by 2 is a 6, and 41. 2 by 1, 2, 3, 4, 5, 6, 7, 8. So that would be 16. That's a lot. Okay, great. So that would be like me going in, grabbing 5 piles that I randomly picked, and then I want to find the average M&Ms per pile. So I just go to my calculator, and I'm going to add those numbers. So we got what? 6 plus 3 plus 9 plus 6 plus 16, divide by 5, and that gave me 8. So I have 8 M&Ms per pile, and that's representing a sample mean or an X-bar. And then all of us in the classroom would be doing this. So each of us, if there was 20 of us, we're each generating 3 samples, so we'd end up with 60 total samples. Okay? So since I obviously don't have everybody with me in this, I'm just going to show you some class data that I got from last year. Before I move on, though, I just want to show you where this would actually graph, because I have a little histogram down here. So this 8 would be included here, because this is between 8 and 9, including the 8. This is between 9 and 10, but including the 9, and so on and so forth. So you got to envision that I get another number here, put it on my graph, another number here, put it on my graph. Okay, so let me pull up my data from last year, or at this point, probably 2019 is the last time I did this. All right, and here you have it. So this is my data from, like I said, probably 2019, and it's just organized a little bit differently here because sometimes students got confused, but the numbers in the upper left were my random digits that corresponded to the pile I picked, and then the bigger numbers are the actual number of M&Ms. So you'll see that in my 3 trials here, I got a 9.2, a 10.4, and a 7.6, okay? Now, what we did was we took my 9.2, and he would be graphed between the 9 and the 10. We took my 10.4, he was between the 10 and the 11. My 7.6 went between the 7 and the 8, and we started to fill it in, and I just started collecting data from students. As I was graphing on this histogram, a student would be keeping track of all of these numbers for us. So they'd be plugging in the 9.2, the 10.4, and the 7.6, and their L1. And then they do a 1 var stat, and they would figure out the mean and standard deviation of all of our sample means in the class, just like how we did the mean and standard deviation of the sample proportions in the baseball problem. So with my distribution, I ended up with a mean of 7.9 and a standard deviation of 2.6. So if I had to guess the average number of M&Ms per pile out of all 100 of those piles, my best guess would probably be about a 7.9. And so here's my little question, what would happen to our mean and standard deviation if everyone in the class generated 5 more of these? It would just start to fill in more. My mean would probably remain about the same for that center, and my standard deviation would remain about the same as well. But if I were to start over and say, okay, you're not picking 5 piles this time, now you're going to pick 10 piles. So I increase that sample size. By increasing the number of piles or my sample size in each M&M sample, that would get my mean to remain about the same, but the standard deviation would decrease, which would mean that this graph would look tighter around the center. It would shrink and become smaller and be less spread, and therefore would have less variability and would give me a better estimation of the true mean of all the M&Ms on the sheet. And that, my friends, is the day 3 notes. So hopefully that helps, especially if you missed class for either an AP or whatever reason. That's my best task at doing this without actually having classroom students in front of me, because this is usually a very hands-on day. The last page in the notes is simply just matching. So which dot plot would go best with the mean and standard, or the sample size, excuse me. So like when I compare, obviously the mean is about the same for all of these, but the one with the lowest standard deviation, you know, if I had to pick between it says my options are sample sizes of 20, 60, or 120. The one with the smallest standard deviation has to be the largest sample size. So the 120 would go with the first guy. He's got the least spread, it's the tightest here, smallest standard deviation. The biggest standard deviation's right down here at 0.110, so that's got to be my smallest sample size, right? It's because that's like the least amount of data per sample. So most spread, greatest standard deviation, and then just like Goldilocks and Three Bears, the one that's right in the middle, That's 60. So that's this one right here. He's got like the medium spread. But again, you can compare. This is way more spread out, as where this is much tighter at the top. And that's what I mean by your standard deviation decreases, variability decreases. It just gives you a more accurate window of where your true population, either proportion or mean you're looking at, in this case proportion, could lie. As we're here, it's kind of a little bit all over the place. And we'll talk more about what that means in the lessons to come.